All right, welcome everyone. So in this video, this will be the last video for this section on inverse matrices. Let's take a look at how we can use inverse matrices to help us solve systems of linear equations. So let's say I've got a system of three linear equations with three unknowns that I've got written out here. So the first equation is x1 plus 3x3 is 2. The second equation is minus 2x2 minus 2x3 is 1. And then the third equation is x1 minus 3x2 plus x3 is equal to 0. We have various ways that we can solve systems of equations like this. One thing that we can do is rewrite this system of linear equations as its equivalent matrix equation. So the matrix of coefficients in this case is the matrix A, which is a 3 by 3 matrix. The top row is 1, 0, 3. The second row is 0, minus 2, minus 2. And the third row is 1, minus 3, 1. So we have matrix A times vector X. In this case, on the right, we've got constants 2, 1, 0. So we have matrix A times vector X is equal to the column vector 2, 1, 0. We would like to solve this system of linear equations. We have various methods for doing that already. But here's how we can use inverses in this process. So I can take this matrix equation, AX equals B. If A is invertible, I can multiply both sides of this equation on the left by A inverse. So now I've got A inverse times AX on the left side, and I've got A inverse times B on the right side. And you want to be careful here. I have an equation over here. And so if we multiply both sides by A inverse on the left, then that is still going to preserve that equality. And now the A inverse times A, this gives me the identity matrix. And so the identity matrix times column vector X is going to just leave column vector X. So it's like we're solving for column vector X. And on the right side, we still have this A inverse times column vector B. So what that would look like in this example is now we've got column vector X is equal to A inverse, and this matrix was the 3 by 3 example that we looked at a couple of slides earlier, and we found that its inverse matrix was given over here. So it had a top row of 4, 4.5, minus 3, a second row of 1, 1, minus 1, and a third row of minus 1, minus 1.51. So we would take A inverse, multiply it by B, and out comes 12.53 and minus 3.5. And I just want to mention on that Colab doc where we worked with inverse matrices on the very previous slide, I put an example for solving this system of linear equations. So here's what we got using inverse matrices. If you were to, for example, use the lin-alg solve function, and you input matrix A and matrix B, so this would be matrix A, and this would be column vector B, inputting those into this function, you will see that you get the same exact solution that we got using inverse matrices. So let me just summarize this process on the very last slide. So in general, if we want to solve a system of linear equations, we can take any system of linear equations and rewrite it as a matrix equation. Matrix A times column vector X is equal to some column vector B. We can take the matrix of coefficients and maybe find the inverse matrix A if it exists. And if it does exist, then we can multiply both sides of this equation on the left by A inverse. And that's going to make the left side of this equation is going to simplify to column vector X. And the right side is going to be inverse matrix A times column vector B. And here we get our solution for this system of linear equations, namely X is equal to A, matrix A inverse times column vector B. There's one caution here, which is this is great if we have the same number of linear equations as we have variables. So recall, only square matrices can possibly have inverses. So this is not going to be a useful strategy if the corresponding matrix of coefficients is not square. If we have more equations than variables, or we have more variables than equations, then you're going to have to continue using augmented matrices instead. But when we have a square coefficient matrix, this is a nice alternative approach to solving linear systems when the coefficient matrix is invertible.